So ladies and gentlemen, using the QC and KC, it will then show you what is happening. Factors that affect the equilibrium constant, the big K value. We know temperature don't change, K won't change. Everyone okay? All right, so temperature is the key. But what about other factors? Why it won't change? And Le Chatelier using QC can explain it. Or whoever come up with this QC thingy can explain Le Chatelier's principle. I forgot who came first. There are basically a lot of scientists talk about a certain concept. And they all have their own way of presenting. Ready? QC, KC, and KP are not affected by changes in concentrations or partial pressure of the reactant in the product. We know. All right, why so? All right, this will, my intern spent a lot of time with my ex-student to draw this graph for you and to input all this. All right, see the example below for Haber process. It will re-equilibrate after some N2 is added to the equilibrium at time equal to T1. When the temperature, again, is being kept constant. All right, by changing the concentration of reactants and products in the system until QC equals to KC. So take a good look over here. Ladies and gentlemen, this is the graph, and the concentration will keep changing. Nothing wrong, right? Nitrogen, all right? If you add a bit, it's at equilibrium. So it's at always been equilibrium, all right? Equilibrium. So if I add some nitrogen inside there, we disturb the equilibrium, all right? We add it in, it will then, okay, decrease itself. All right, hydrogen is also a what? Hydrogen is also a reactant, all right? So you also decrease, but you never do anything to it, so it decreases from here. Ammonia is a product, all right? You will get more and more over here when it approaches T2, second equilibrium. Now, so over here, based on the value, all right, I put it into a table for you to see. If we're going to track, all right, because a bit low for me, huh? But let's finish this. At the initial equilibrium, all right, which is all the way to T1, this section, right? What is the QC? Once again, right-hand side value divided by left-hand side value. All right. So you have that value divided by this value. For example, you get a value of 0.3. And I'm pretty sure that the QC there will be equal to our KC because it's at equilibrium. All right. Now, we add something to disturb it. Some N2 is added, so the equilibrium is subjected to a disturbance. Okay? And based on the T1 itself, right, this arrow down, take a look at what happened at the points that which I use a graph and the actual value here to show you. The QC at the point, all right, the ammonia is 2, but the bottom will become 1.55. All right, the value has changed basically. And your value of your QC is no more a 0.3. It becomes 0.1. So it's smaller than the KC. And you think of Le Chatelier say what? I increase N2, right? Forward reaction is favored. QC shows it. The other group of scientists. Can everyone? Smaller, you push it to the right-hand side. Yes? So your POE, position equilibrium, shift to the right, which is here. Around the color. By Le Chatelier's principle, position equilibrium shifts to the right so as to decrease the N2. As you can see in the graph, where your N2 and your H2 decreases, while NH3 increases. The NH3 is the numerator, the N2 and H2 is the denominator. Makes sense? My QC should go up. Everyone okay? So the value will approach 0.3 from 0.1. Right? Clearly shown. Very easy to understand. And then at the where? At the second equilibrium, this point, right? T2, where it starts to become constant. Let's see what happened. All right? With the value on the graph. When you reach a new equilibrium, using the values on the graph, the ammonia will be somewhere around here, 2.36. And the other two values here will be this value after I multiply together. And then at equilibrium, the QC will be 0.3 again. So all in all, you explain what the Chatelier has been telling us, thereby the concentration of reactants and products have adjusted themselves to partially remove the disturbances, such that at the new equilibrium, I'm very sure that the QC will be equal to the KC again.
It is like guaranteed.
Guaranteed, according to the concept, guaranteed. You learn, I learn.
That's like, no matter how much into you add.
It's like that. He came up with this.
No matter how much into you add, it will always be like.
Yes, it just takes time. So in summary, a change in concentration affects the position of equilibrium. Yeah, I repeat myself. When you change concentration, you affect the position of the equilibrium. The POE did shift, but it does not change the value of the big K. Therefore, did the equilibrium composition change? This is where the MCQ all come out to Q already. I tell you, structured questions is easier most of the time. It's an MCQ. Did the value we use the same? You look at the graph. Did the value go back to the same? No, it didn't. Do you realize the same value here you get called 0.3? It was based on a, let me show you, the 0.3 and 0.3. Okay, that's why I brought this out. You got to appreciate it, and this is the best way to appreciate this presentation, I believe. 0.3, 0.3, right? You take a look at the QC you calculated. The top over here is based on what? It was based on a value of 2 to the power of 2. But over here is not. It's not the same value. The bottom also not the same value. But two different value, you can divide to get you the same value. Makes sense. Are you with me, my friend? Careful, okay? Can, So that's what I want to show.
So POE different by KC same.
Yes, all right. So all in all, what happened when you increase the concentration, all right, increase concentration of a reactant, for example, correct? Which is what is happening here. Okay? So let's summarize it and close it already. Number one. Okay? What happened over here? The position of equilibrium shifted. Make sense?
To the right.
Yeah, to the right, blah, 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 to the right-hand side. Okay, the position of equilibrium shifted, okay, to the right. Then, obviously, the equilibrium concentration also has changed.
For all.
Make sense? Don't confuse with the definition of dynamic equilibrium. Understand what I'm saying? Dynamic equilibrium is a concentration, stay constant, never change. So be very clear. Yeah. And however, what happened? The K value remains constant.
What did they use?
That's it. Okay? Clear? Make sure we know the connection yet the differences. That's all. And then actually you'll finish already. Be very, very clear. Okay? So you realize in order to show all this, we got to show you the KC. What is happening over here. The QC, I mean, and the QP. Can everyone? Okay, So that makes sense, right? So the concentration will change, all right? After you disturb it, it will change, right? Because the position of equilibrium have shifted. But coincidentally, I don't know what the word, coincidentally, this divided by that, it will give you the same K value if your temperature don't change. Am I okay? Make sense? If you would like to catch my latest videos, click on subscribe button right now. And click on the bell if you want to receive instant notifications once I've uploaded my latest video. If you would like to join my live chemistry classes and revision workshops, go on to winnerseducation.com and find out how you can score distinction for chemistry on a consistent basis, either in our center or online via Zoom. If you want to check out my online school, go on to passwithdistinction.teachable.com. You'll be able to learn chemistry concepts at your own pace and anywhere in the world, topic by topic. This is Sean Chua from Winners Education, to your distinction in chemistry.